what actually procedure modeling means, that we construction 3D models with algorithm with procedures, and there are small programs which you can connect it together to describe, for example, overall surface property of a 3D model. So that's happens purely digital, purely with computer, and it could be applied with a lot of automatic. And our tool we're using is Houdini engine, and it's a long-term 3D content creation tool since 90s, and this tool was used in a lot of Hollywood production, in movie production, and now we could take the advantage of this program to model the 3D models easily. And this tool is also for indie developer very interesting because they are very indie friendly. It's cost only $99, so you can just take an indie license and use it for your big content production. And the reason why we are doing procedural modeling is that sometimes we don't just have enough time to make everything by your hand. So this is some example from a 3D asset in Houdini. You can see we just describe with mathematic patterns the surface properties. You can see I can extrude areas and surface from elevation properties, and step by step to create complex looking surface. This is another side. And sometimes algorithm even surprise you. And there's always some errors, but it's looking interesting. I like some errors from my procedure because it's always surprising. This is look for me two little animals meeting up in the strange planet. But you got a little bit hard time to make your content 3D models looks from real life. So it's more, my planet is more fantasy planet. So there's another pictures. But the procedural modeling method could be also combined with scanned data. In this example, we modeled the Mars surface based on the digital elevation model from NASA. NASA has just scanned all the surface data in very high resolution, but the problem is you cannot get all of this data in your game. It's more than 3-4 gigabyte size, but we combining this data with our procedures. That means you can look at Mars from far distance. It looks quite good, but if you are going into the valley, it's just the resolution of the data just limited. So we have to do some procedure to refine the details. You can see the camera looking at the marked surface and divide in different distance area. So if the area near to the camera, you got more polygons to describe the details. So that's another picture. And we use a very good terrain framework. It's Proland. It's from French, and it's very performant, and you can combine a lot of procedures with analog data, like from NASA. So that's it.
Any questions about that, about procedural modeling? Okay, one thing I want to talk about next is depth cameras, which probably some people have heard about the Microsoft Kinect and the Intel RealSense, right? The thing that we really love to work with those is because we get point clouds. So one of the things that you normally do when you do like a normal filming, you just get a two-dimensional plane, right? Just one film. But what happens if you want to include a film in your 3D game? Then it gets very hard. So what you can do is combine a depth camera. That means a camera that not only gives you like a RGB, so a normal color image, but that also gives you distance from the camera to each pixel. So for instance, if I look in that direction, maybe this would be 1 meter away and something behind it would be like 2 meters away. So for each pixel, it tells me how far it is away, roughly. And so what you can do is map the color image, so the image that you get, like a webcam image, onto the 3D surface. So actually you get a three-dimensional nose, lips, and everything else out of it. And there was a guy like a couple of years ago who did DeathKit that did exactly that. He used a DSLR in combination, who was filming, in combination with a Kinect. And those two together give you a three-dimensional film. Of course, it's limited because you're just going to film from one direction, so everything behind you is just not existence. But everything that's, here on the front, you still get in 3 dimensions. So what we want to use it for in one project, for instance, is, you probably know Gravity. And in Gravity, everything is fake. It's just 3D models and VFX. But one thing that isn't fake is the faces. So they built a really elaborate and hard to build rig to get all the people spinning, to get all the lighting correct. But one thing they did in the end was just get the right camera angle of the right person's face and then combine that with a 3D imaging that they did beforehand. So everything was fake except for the faces, and then they still had to do a bunch of things to get it into the scene. So what we want to do, because we're doing mostly VR content, we want you to be able to look from different directions. And so the moment you have a 2D image from a normal film camera and you look from it from the side, you immediately see that it's just a 2D image. But if you go ahead and just use the 3D imaging from the last thing and just film the head and put it into a 3-dimensional suit, so just a 3D model of a suit, and then put the face that is filmed inside of it, then all of a sudden you got a 3D model. So in VR, then in the end, you can walk around the astronaut suit, look at it from any direction, and you see that the face is filmed from a real actor, so you get all the real emotions that you normally, it's really hard to capture in motion capturing, because all those little facial details are really hard to capture. But so you can combine those two, and you get filmed 3D imaging combined with 3D models from the suit. And then you have a really cool model for your VR game. And if you want to go one step further and want to get rid of like the 180 degrees that you couldn't see because the camera was just coming from one angle, then you have to go one step further and do something like point cloud fusion or viewpoint video. And also Microsoft has done some, a lot of research recently into that. And what they came up with was filming people from all different directions. You see all the cameras with depth imaging and normal cameras, RGB cameras. And they combined it in something like photogrammetry. So they're basically combining all the photos, all the videos into images that are 3-dimensional. And they get this kind of a mesh out of it. And then they're cleaning the mesh. They're even going so far as to do different kind of resolutions for different body parts. Because, for instance, for the main part of the stomach or so, you don't need the kind of resolution that you need for the face. Because we humans are really just looking at the faces and recognizing immediately if something is wrong. And there's so much detail in the face that you have to render that they took special care about it. So in the end, you get a three-dimensional video. That means you're really capturing someone in a studio, and you're looking at those videos from all the different angles. And you can just go ahead and put it into your three-dimensional scene and have someone walk around. So and then you get to the moment where you can actually produce films, or even interactive, if you go one step further, content that is really filmed. So all those kind of holodecks where you were walking around with, you know, this becomes a reality once that kind of technology becomes available for the public or for, you know, greater audience. And on the more low-cost end, already the Augusburg software that I was telling about you before about photogrammetry does that. And this, for instance, was taken with something like 30 DSLR cameras. So, you know, if you have 30 DSLR cameras handy, you could try that out yourself and film it from different angles and get a three-dimensional representation of the film, which is pretty cool to do. Okay, but we're not all, you know, just interested in that. We're also interested in motion capturing because, you know, you sometimes need those 3D models. Except if there are any questions. Okay.
Thank you. Different motion capturing methods, and I will introduce you the more classical one. And we just reduce motion in a few points. And in our case, to capture full body motion, you need 18 sensors. In our case, we have an in-house tool who combine two different systems. The first one is you got 18 points. That's small gyro sensors. It's from your smartphone, so it's very popular in production. So that means it's quite cheap. And this sensor has mostly accurate rotation measurement. So we could use this sensor on actor's body without any problem with occlusion. You can imagine in motion capturing, the actor has always been seen from outside of the 3D room. In classical motion capture production, you need a lot of cameras, about 40, 50 cameras around our area. And this lot of cameras, this makes the system very expensive, like the Vicon system in a lot of AAA production. So we use the sensor alternative to lowering the price, but the result is actually not comparable with AAA production. So we have to improve the data, and in optical tracking system with camera, you got very accurate positioning tracking, and that is what the first system cannot do. So we combined, like Nico says, with DPS cameras, with RGBD data, and on this kind of data, this data from this kind of DPS camera are very good in position and tracking. So you get small pixels in the camera image, but this picture could be very good tracked all the time. Another case for the sensor is as a rotation, and so you need a lot of optical reference to calculate the rotation. So why not we combine the data of the both system? So that is loosely what it's about. So I can show you a small example. Yeah. It's just it in a random. We put a real motion capture data in a random model. It's just it's from a kung fu master. But you can do it for funny things, combine impossible things together. Okay. So in this video, you can see the small sensors of the gyroscope sensors. And on the four corner, you can see our Kinect camera, which give us more accuracy in position tracking. So that's it. Thank you.